Good morning. So we'll continue the numericals from the module 2, which consisted of bars, and now we'll take up the analysis of trusses. So what are truss elements? Truss elements are again load bearing elements, but these truss elements, though they behave as one unit, they consist of number of beams which are connected at their endpoints. We call those endpoints as joints, and we assume that the load that acts only on the joints, and if there are any other particular forces acting, we consider it to be axial loads. We don't take into consideration the bending loads for trusses. The best example that we can relate to for trusses are the bridges that we come across. May not be the bridge that we see in Karnataka, but the beautiful example is the Howrah Bridge in Calcutta, wherein it looks like this. These are more similar to the truss elements that we will be dealing with. So going with the steps that needs to be considered, there are a number of steps that we take. Just like in bars, we also consider a few steps in trusses. But remember, no matter if it is bar, if it is a truss element, or even if it is a beam and a shaft, which we will come across in the next module, the steps that we follow are more or less the same. So what is the first step that we do? The very first step that we come across is formulate the finite elements, or it will be also stated as modeling of a given numerical into finite elements. So what exactly do we do in this? Suppose, let us consider a simple truss element like this given. The question may also give you some amount of thickness to it or a cross-sectional area. Now, we need to convert this given numerical into finite element. So, how do we convert this? We'll assume, or we'll give number to the number of beam elements that are present. For example, this has only 2 beam elements, so we'll consider those to be the elements. Since there is no force acting in between, we'll take those entire beam elements as one finite element. So how do we model this? We will model 1, 2. Node numbering. Again, if I use a different colored chalk for this, so this will be numbered as 1, this will be 2, this will be 3, and when I want to write the finite elements separately, I can do it as This is 1, 2, the nodes being at these locations. And a number the element as 1. Now similarly, for the second element, I can draw the element separately. This is 2 and this is 3, and the element number being 2. So element 1 and element 2. Now if we consider the elements separately, the load that is acting will also be mentioned. Some N, F2. Once we have done the finite element, next we need to calculate the element stiffness matrix. As I told you, no matter what the problems are, the problems it can be on bars, it can be on trusses, it can be on beams, it can be on shafts, even problems related to thermal conditions. The very first step that you do is you will convert the given numerical into finite elements. Once you have converted it into finite elements, next you will calculate the element stiffness matrices. That is the second step. After finding the element stiffness matrix, you will find out the global stiffness matrix, considered to be step 3. Once global stiffness matrix is determined, you will substitute it to the equilibrium condition. Equilibrium condition consists of K into Q equals F, where K is the global stiffness matrix, Q is the global nodal displacement vector, F is the global force vector. So this is the fourth step. First step is you will be converting the given numerical into finite elements. Second step, you will formulate the element stiffness matrices. The third step, you will assemble the element stiffness matrices to obtain the global stiffness matrix. The fourth step, with the obtained global stiffness matrix, you will formulate the equilibrium condition, which is given by K into Q equals F. So these are the first 4 steps. Once you have completed this, the fifth step is you will apply the boundary conditions, and you will also use any one of the methods of handling the boundary conditions. So we are discussed in bars. There are 2 types of methods that are employed for handling the boundary conditions. The first condition is elimination method, or the first method is elimination method. The second method is penalty approach method. So after bars, with your syllabus in view, we don't go with penalty approach method any further. We only go with elimination approaches. So remember, so once you have done the equilibrium condition, you will apply the boundary condition and take up the elimination method. Once from the elimination method, the sixth step is you will obtain the displacement values. The last step is, if it is related to structural members like bars and trusses, we will obtain or calculate the stress in those particular elements. So these are the only 7 steps that you come across finite element solution of problems. So the first step is, again I repeat, modeling the given numerical as finite elements. Second step, you will calculate the element stiffness matrices. Third step, you will assemble the stiffness matrices to obtain the global stiffness matrix. Fourth step, you will assemble the global stiffness matrix with the load vector and force vector that you have obtained, and then obtain the equilibrium condition. From the equilibrium condition, the fifth step is you will substitute the known boundary conditions, and you will either take up elimination method or penalty approach method of handling the boundary conditions, and from that the sixth step is you will obtain the displacement values. So once the displacement values are known, the seventh step, if required, we will calculate the stresses and reaction and supports. So in stresses, if we continually say discussion for an element that we consider, for example, I keep this as the example and take only one element to discuss further. This is node 1, node 2. For the purpose of generality, I will name these as I and J, or even if you want to, you can put it as J and J plus 1. So if J takes the value as 1, the node number at this location will be 1. This will be J plus 1, which is equal to 2. Now this will be called as element 1. Now, as I told you, we assume that all load acts on only the joints of the trusses. So the load will act only on the nodes that are present. So suppose there is an axial load acting at this node. I'm sure if it is visible to you. So there is a force which is acting axially on the member. Now we will simplify these loads to be, or will consider the force components of this particular load along x direction as well as along y direction. Okay, so what will be the force if this is called as F? Even brighter. If this force is F, then the force acting along the component of F along x direction, we will name it as F suffix x, and the force component of F along y, name it as F suffix y. Now, what is F suffix y and F suffix x? If we consider this to be theta, then Fx will be equal to F cos theta. And this F sin theta. So the component of F along y direction is equal to F sin theta, and the component of F along x direction is F cos theta. Why are we calculating this? We will be calculating the degrees of freedom or the displacement of node 1 and node 2, or J and J plus 1 along the x direction and along the y direction. So hence, in order to do that, the component of forces along the x direction and y direction we try to determine. These will result in something called as directional cosines. The second step, when it comes to the analysis of trusses, we cannot directly calculate the element matrices unless we know the values of directional So in order to calculate the values, we will determine the positions of node 1 and node 2 with respect to x and y coordinates. For example, this is marked as x1 comma xy1. If node j is having the coordinates x1 and y1, and node j plus 1 is having coordinates x2 comma y2, then the value of L is given by L is cos theta, and value of cos theta is x2 minus x1. This, if I want to simplify the diagram for you, how is it x2 minus x1 divided by L suffix e? So how do you get this? For the element that we are drawn, so this is theta, and the coordinates we will consider only the x coordinate, because we want the adjacent side by hypotenuse as the required measurements to calculate cos theta. This is x2, this is x1. The entire length of the element will denote it by L suffix e, where e denotes the element number. So this entire length is L suffix e. So cos theta will be equal to this is the length that we need. This is x2. So x2 minus x1 divided by L suffix e. So this is equal to L. The directional cosine value of L is cos theta, which is equal to x2 minus x1 by L suffix e. Now M is equal to sin theta, and sin theta is given by y2 minus y1 by L suffix e. So the value of y1 corresponds to node 1 and y2 corresponds to node 2. So this is x1 comma y1. So if I want to calculate sin theta, it will be opposite side by hypotenuse, opposite side y2 minus y1. So sin theta is given by y2 minus y1, entire thing divided by L suffix e, where L suffix e is the length of the given element. Now, how do we calculate length of the element? L suffix e, how is it calculated from the given coordinate values? Coordinate values are x1, y1 and x2, y2. From these coordinate values, how do we calculate the length of the element? L, e. If you use the Pythagoras theorem, square of the other two sides of a right angle triangle, if you add it, then you will obtain the square of the hypotenuse. Now L e square is equal to x2 minus x1 whole square plus y2 minus y1 whole square element. So now we have calculated LE, or if you want only LE, it is root of x2 minus x1 whole square plus y2 minus y1 whole square. We know the value of length of the element LE. We know the values of directional cosines L and M. So L is given by a cos theta x2 minus x1 by LE. Sin theta, which corresponds to the directional cosine M, is given by y2 minus y1 by LE. So L, M and LE are known. With this, we will proceed to formulate the elemental stiffness matrices. So I will be wiping this. So please, I hope you have taken down it in your notes without writing it. If you just watch the video, you will not be able to understand. The elemental stiffness matrix, keeping this, I will try to formulate. So elemental stiffness matrix is given by, or address element. For the bar element, it was A E by L into 1 minus 1 minus 1 and 1. The same stiffness matrix doesn't apply for a truss element. Please do remember, you cannot use the same formula. Elemental stiffness matrix is given by again small k suffix e, where the suffix e denotes the element number. So small k suffix e is equal to, I hope it is legible. Yes, small k suffix e is equal to a suffix small e suffix small e divided by L suffix small e. So A denotes the cross-sectional area of the truss member, that we have considered a particular element in the entire truss. E, capital E, denotes the Young's modulus of that particular element. Small l, as we have calculated, it denotes the length of the finite element, multiplied by you need to remember the matrix. So how do you remember the matrix? Different people remember it in different ways, but for me it is easier to remember first the diagonal matrix and then formulate the other elements in the given matrix. So what is the diagonal matrix that comes into picture? It is L square, then M square, again L square, and again M square. So what are these L and M? L and M are the directional cosines. So L square, M square, L square, M square. Next, the stiffness matrix, they are always symmetric in nature. Please do remember it. Stiffness matrix is always symmetric in nature. What does symmetric in nature mean? The elements on the upper half of the diagonal will be the same as the elements on the lower half of the diagonal. So next, it is ln the multiplication of both directional cosines and minus L square. The third element in the first row is minus L square, and the last element, the fourth element in the first row is minus square ln minus L square minus ln, that is the other way of remembering it, but I will suggest L square L square L square L square. We finish the diagonal elements first. After that, remember the second element in the first row to be the product of both the directional cosines ln. The first two elements in the first row repeat the same for third and fourth element, but with a sign change or the negative of it. Next, minus ln is here, minus ln minus L square. This is its third method of, so the second row to be completed. So whatever minus ln was present as the fourth element in the first row, we have substituted as the third element in the second row. So it is the other diagonal for the matrix. Repeat the same term, and minus L square you will repeat it on the diagonal direction. And the last term in the upper half of the diagonal is ln, which remains right here. I'll again formulate the diagonal matrix for you. How do you remember the diagonal matrix for a truss element? Remember the directional cosines. Once the directional cosines are known, first fill the diagonal elements. So diagonal elements L square, L square, L square and N square. Once the diagonal elements are completed, remember the product of both the directional cosines will be the second element in the first row. So once the second element is filled, the negative of the first two elements will be substituted as third and fourth element. Once you have done with the entire first row, coming to the second row, minus ln is present as the fourth element in first row. Repeat it in the other diagonal direction. Minus ln ಇಲ್ಲಿ minus L square ಏನಿದೆ ಅದನ್ನ ಸೆಕೆಂಡ್ ರೋ ಲಾಸ್ಟ್ ಎಲಿಮೆಂಟ್ ರಿಪೀಟ್ ಮಾಡಿ ಉಳ್ಕೊಳ್ಳೋ ln ಮೇಲ್ಗಡೆ ಫುಲ್ ಟರ್ಮ್ ಏನು ನೀವು ಹೊಸದಾಗಿ ಬರೋದ್ರೆ ಡಯಾಗ್ನಲ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಆದ್ಮೇಲೆ ಅದರಲ್ಲಿ ಉಳ್ಕೊಂಡಿರೋ ಕೊನೆ ln ನ ಫೈನಲ್ ಸ್ಲಾಟ್ ಏನಿದೆ ಆ ಡಯಾಗ್ನಲ್ ಅಪ್ಪರ್ ಹಾಫ್ ಅಲ್ಲಿ ಅಲ್ಲಿಗೆ ಫಿಲ್ ಮಾಡಿ. ಸೊ ದಿಸ್ ಕಂಪ್ಲೀಟ್ಸ್ ದಿ ಅಪ್ಪರ್ ಹಾಫ್ ಆಫ್ ಯುವರ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್. ಸೊ ಒನ್ಸ್ ದಿ ಅಪ್ಪರ್ ಹಾಫ್ ಇಸ್ ನೋನ್, ಮತ್ತೆ ತಿರ್ಗಾ ಲೋವರ್ ಹಾಫ್ ಅಲ್ಲಿ ನಾನು ಹೇಳಿದಂಗೆ ನಿಮಗೆ ಸ್ಟಿಫ್ನೆಸ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಇಸ್ ಸಿಮೆಟ್ರಿಕ್. ಸೊ ಇಲ್ಲಿ ln ಇದೆ, ಇಲ್ಲೂ ln ಬರೀರಿ, ಮೈನಸ್ ln ಇಲ್ಲಿದೆ, ಮೈನಸ್ ln ಇಲ್ಲಿ ಬರೀರಿ, ln ಇಲ್ಲಿದೆ, ln ಬರೀರಿ, ಮೈನಸ್ L ಸ್ಕ್ವೇರ್ ಇಲ್ಲೂ ಅಷ್ಟೇ, ಇಲ್ಲಿ ಮೈನಸ್ ln. ಇಲ್ಲ ನಿಮಗೆ ಲೋವರ್ ಹಾಫ್ ಫಿಲ್ ಮಾಡಕ್ಕೆ ಕಷ್ಟ ಅನ್ಸಿದ್ರೆ ಫಸ್ಟ್ ರೋ ಏನಿದೆ ರಿಪೀಟ್ ಇಟ್ ಆಸ್ ದಿ ಫಸ್ಟ್ ಕಾಲಮ್. ಸೆಕೆಂಡ್ ರೋ ಏನಿದೆ ಸೆಕೆಂಡ್ ಕಾಲಮ್ ರಿಪೀಟ್ ಆಗಬೇಕು. ಥರ್ಡ್ ರೋ ಏನಿದೆ ಥರ್ಡ್ ಕಾಲಮ್ ಏನಿದೆ ಥರ್ಡ್ ರೋ ರಿಪೀಟ್ ಆಗುತ್ತೆ. ಫೋರ್ತ್ ಕಾಲಮ್ ಏನಿದೆ ಫೋರ್ತ್ ರೋ ಆಗಿ ರಿಪೀಟ್ ಆಗುತ್ತೆ. ಸೊ ಆ ತರ ನೆನ್ಪಿಟ್ಕೊಂಡ್ರೆ ದಟ್ ಈಸ್ ಆಲ್ಸೋ ಫೈನ್. ಸೊ ದಿಸ್ ಗಿವ್ಸ್ ಯು the elementary stiffness matrix. So why do we have 4 cross 4 matrix for a truss element rather than a 2 cross 2 matrix? So past problem ನೀವು ನೋಡಿದ್ರೆ the stiffness matrix was 2 cross 2. ಅಲ್ಲಿ elementary stiffness matrix ಅಲ್ಲಿ ಈ AE by L it is a common term ಬಿಟ್ಬಿಡಿ. ಅದರ ಒಳಗಡೆ matrix multiply ಮಾಡೋದ್ರಿಂದ the matrix remains as 2 cross 2 only in bars. But ಇಲ್ಲಿ it is 4 cross 4. As I told you, we can denote the global degrees of freedom on this stiffness matrix. So bars will ತಗೊಂಡಾಗ bars had only displacement in one direction. So ಇಲ್ಲಿ this is a bar and there was a force acting. The displacement used to be only along x direction. There is no displacement along the y direction. So degrees of freedom was only one for one particular node. So two nodes which constitute one element, they had only 2 degrees of one degree of freedom at node 1, the other degree of freedom at node 2. So hangage 2 cross 2 matrix was prevalent. But now when you consider a truss element, there is a displacement along x direction as well as there is a displacement along y direction for one node. So node 1 can get displaced along x direction as well as get displaced along y direction. Degrees of freedom for one particular element. There are two nodes. Each node has 2 degrees of freedom. So ಎರಡು node ಇಂದ total ಆಗಿ there are 4 degrees of freedom. So 1, 2, 1 and 2. So when you have 4 degrees of freedom, the stiffness matrix will also consist of 4 cross 4 matrix. Now, how do we denote? Last time ಅಂದ್ರೆ ಒಂದು ಎಲಿಮೆಂಟ್ ಒಂದೇ degree of freedom ಇತ್ತು. ಆ ಏನು ನಂಬರ್ ಬರೀತಾ ಇದ್ವಿ, it was to correspond to the displacement of that particular node itself. But ಇಲ್ಲಿ it is quite different. If I take, I hope this is also visible here. Let me say this is an element. This is node 1 and this is node 2. J plus 1 ತಗೊಳ್ಳೋದಾದ್ರೆ, if I call this as, we have a J plus 1 ಪಕ್ಕ diagonal, we will retain it. So ಅಲ್ಲೇ ಇರುತ್ತೆ. The general formulation is 2J minus 1. So ಇಲ್ಲಿ degree of freedom along x direction we represent it as 2J minus 1 and the displacement along y direction, degree of freedom along y direction we represent it as 2J. So ಇಲ್ಲಿ ಇನ್ನೂ ನೀಟಾಗಿ ಬರೆಯಬೇಕು ಅಂತ J plus 1 ಬದಲು this 2J minus 1 for the displacement along x direction. Numbering I written down. This is displacement along y direction will be equal to 2J. So when I substitute the node number as 1, 2J minus 1 will give me 1. 2 into 1 minus 1. 2J will give me the value 2. Similarly, J plus 1, if J is equal to 1, J plus 1 is 2. 2J minus 1 at this location. 2J minus 1 and this is 2J. So 2J, 2 into 2 is 4, 4 minus 1 is 3 and this is 4. So if ಏನು why is it required? You global stiffness matrix na formulate ಮಾಡಬೇಕಂದಾಗ, if you remember the bar problem, the terms that are common ಅದನ್ನ ಆಡ್ ಮಾಡ್ತಾ ಬರ್ತೀವಿ. ಇಲ್ಲಿ ಆ degrees of freedom ಮಾರ್ಕ್ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ this is 1, this is 2, 3 and 4. Remember, bars number used to be or it can be considered as the degree of freedom of that particular node itself. So that doesn't hold good. Bar there was only 1 degree of freedom for one node. Illi one node ge 2 degrees of freedom ಇದೆ. One along x direction, one along y direction. So ಏನಾಗಿದೆ, 1 and 2 both denotes the degree of freedom for node 1. 3 and 4 denotes the degree of freedom for node 2. So again 1, 2, 3 and 4. ಇದು ಯಾವಾಗ ಯೂಸ್ ಆಗುತ್ತೆ? Suppose there is a second element. There is one more element. ಇದ್ದಾಗ 2 ಗೆ ಡಿಗ್ರೀಸ್ ಆಫ್ ಫ್ರೀಡಮ್ ಎಷ್ಟು ನಂಬರಿಂಗ್ ಇರೋದು 3 and 4. ಸೊ ಇಲ್ಲಿ 3 4 ಆಗುತ್ತೆ. 3 ಗೆ if you substitute 2j minus 1, 2 into 3 6, 6 minus 1 is 5. So ಇಲ್ಲಿ 5 ಬರುತ್ತೆ. 2j is 6. So 5 and 6 ಬರುತ್ತೆ. When you take up a problem, you get to know. But right now remember 1, 2, 3, 4 is only for element 1 having node number as 1 and 2. So this completes how to formulate the element stiffness matrix. I will erase stuff which you have taken to calculate LD and LNN. Now, once we know the element stiffness matrices, we will calculate the global stiffness matrix. So once the element stiffness matrices are formulated, global stiffness matrix is to be created. So formulate global stiffness matrix. What is this global stiffness matrix now? Small or capital K is equal to summation of all small k's, where E from 1 to n. So suppose you have only 3 elements, K will be equal to capital K, K1 plus K2 plus K3, small K1 plus small K2 plus small K3. So once we have formulated the global stiffness matrix, the next step would be to formulate the global nodal displacement vector. Formulate global nodal displacement vector. Each node has 2 directions for getting displaced, one along x direction and one along y directions. As we had previously discussed, the values that Q gets are 2 in number for each node. Q is equal to, I'll consider only one element for now, Q1, Q2, Q3 and Q4. Last time discuss madanga, there is one element, it can get displaced along this direction as well as along y direction. Similarly for the other node, the yellow node is this will be 2j minus 1, 2 into j, 2j minus 1, 2 into j. Here in 2j minus 1 ಅಂತ ಇನ್ನೂ ಯೋಚನೆ ಮಾಡ್ತಾ ಇದ್ರೆ, it is nothing but the number that are used to denote the degrees of freedom. One element number 1 ಆಯ್ತು ಇಲ್ಲಿ ಅಂದ್ರೆ 2 into 1 minus 1, 1. So Q1 ಇಲ್ಲಿ ಬರುತ್ತೆ, 2 into 1, 2, Q2 will be along y direction. Second node illiದ್ರೆ 2 into 2 is 4, 4 minus 1 is 3. So this is Q3. Illi 2 into 2 is 4, Q4 is along y direction. So Q1, Q2, Q3 and Q4. So that is what we have formulated. Similarly, once the global nodal displacement vector are known, we will 4 transpose. I hope everyone are aware of what transposes matrix ಅಲ್ಲಿ. So ನಾವು ರೋ ನ ಬರ್ದಿರೋದನ್ನ ಕಾಲಮ್ ಅಲ್ಲಿ ಬರೀತೀವಿ, ಕಾಲಮ್ ಅಲ್ಲಿ ಬರ್ದಿದ್ರೆ ಟ್ರಾನ್ಸ್ಪೋಸ್ ಹಾಕಿದ್ರೆ ರೋ ಬರೀತೀವಿ. So this is what it is. So now global force vector ಕಂಡುಹಿಡಿದಾದ್ಮೇಲೆ the equilibrium equation formulate ಮಾಡ್ತೀವಿ. Equilibrium equation is given by the same whatever we had previously discussed. So equilibrium equation equilibrium equation is given by K into Q is equal to F, where K denotes the global stiffness matrix, FQ denotes the global nodal displacement vector, F denotes the global force vector. So KQ equals F, we will substitute. After that, apply the known boundary conditions. Apply the boundary conditions and use, from the examination point of view, the penalty approach method will be limited to the bar problems. From here on, we take up the elimination method, but there is no restriction that they will not ask you, but it is seen that the majority of the times it is only elimination method that is asked for truss elements. And use elimination method of handling boundary conditions. To determine the displacement. So after creating the equilibrium condition, we go with the elimination method of handling the boundary conditions. The boundary conditions can be the displacement whose values are known. A fixed node will have a displacement equal to 0, or as we have seen in the last problem of bars, a particular node can have a given displacement as well. So you will substitute this to obtain the unknown displacements. Once the unknown displacements are known, you can calculate the stresses in each element. Stress in each element are calculated by the formula sigma E equals capital L suffix C by L suffix E minus L minus M L N, row matrix multiplied by the displacement vector Q1, Q2, Q3 and Q4. So sigma equals stress for the small e denotes the element number, capital E denotes the elastic modulus which will be given, L small l denotes the length of the given element. So sigma E equals EE by LA multiplied by minus L. This small l and M denotes the directional cosines. Don't get confused with the small l and small l suffix E. Small l suffix E denotes the length of the element. Small Small l denotes without the suffix, it denotes the directional cosine. So minus L and n multiplied by the displacements that will be calculated Q1, Q2, Q3 and Q4. So this formula will give you the stress. So suppose if you are calculating it for element 3, you can substitute small e as 3, sigma 3 equals E3 by L3 minus L, L and n, Q1, Q2 and Q3. L and m keeps on changing for each element. So when we take a problem, you get a better idea. We generally formulate or we tabulate the values of L and m initially in the problem for all the elements, and then we proceed further to calculate the element stiffness matrices. Okay. Once stresses are found, we can now find the reactions at support. Reaction forces at support. The formula again is the same that we have used for the bars. R vector is equal to K multiplied by Q minus F, where capital N denotes the global force vector, Q denotes the global nodal displacement vector, K denotes the global stiffness matrix, R denotes the vector corresponding to reactions at the different node locations. So these are the 9 steps that you will follow to solve problems on truss elements. In the next session, we will take up the first problem and then proceed with its solution. Thank you.